Natural gas is extracted from oil wells, coal beds, natural gas fields, and landfills. After processing, natural gas contains a mixture of hydrocarbons, between 70 and 90% methane, between 5 and 15% ethane, and smaller amounts of propane and butane. Combustion of these hydrocarbons releases carbon dioxide and water and produces chemical energy. Natural gas has a very low energy content at normal atmospheric pressure. Carrying a sufficient amount of gas to power a vehicle any distance would take a huge storage tank. Therefore, natural gas for transportation is pressurized to several hundred atmospheres. This compressed natural gas still has a quarter or less of the energy content of gasoline and thus requires larger storage tanks at refueling stations and on the vehicles themselves. Refueling of compressed natural gas vehicles is also slower than liquid fuels, requiring several minutes to fill the tank. On the plus side, natural gas costs less on the world market than gasoline or diesel fuel. Natural gas deserves its reputation as a clean fuel because it produces fewer particulates, non-methyl hydrocarbons, and NOx, nitrous oxides, during combustion than gasoline or petrodiesel. Buses in areas suffering from air pollution are often powered by compressed natural gas and may be distinguished by the large storage tanks on their roofs. Most urban areas in the United States have compressed natural gas refueling stations. For example, California now has more than 200 compressed natural gas refueling stations. More importantly, from the perspective of this video series, combustion of natural gas emits smaller amounts of greenhouse gases than any fuel except for hydrogen. Leakage of natural gas during extraction, refining, distribution, and combustion is an issue because its main constituent, methane, is a greenhouse gas with 23 times the global warming potential of carbon dioxide. Such leakage is small, however, and typically compressed natural gas vehicles emit about 12% less greenhouse gases than gasoline vehicles. George W. Bush, the 43rd President of the United States, declared in his State of the Union address of January 28, 2003,
"A simple chemical reaction between hydrogen and oxygen generates energy which can be used to power a car, producing only water, not exhaust fumes. With a new national commitment, our scientists and engineers will overcome obstacles to taking these cars from laboratory to showroom, so that the first car driven by a child born today could be powered by hydrogen and pollution-free."
Today, most experts agree that this assessment was overly optimistic given the technological and logistical problems that remain unresolved. 50 years, not 15, would be a more reasonable timeline for some general use of hydrogen as a fuel for transportation. Internal combustion engines with some modifications can burn hydrogen, but the thermodynamics of such engines limits their efficiencies to 23%. This means that less than a quarter of the energy in the hydrogen is converted into propelling the vehicle. Fuel cells in which hydrogen reacts with oxygen to form water and generates electricity for an electric motor that moves a vehicle may be more efficient, theoretically above 36%. This approach, however, depends on advances in hydrogen storage, fuel cell costs, fuel cell reliability, and hydrogen production and distribution.